Hey everyone, in this video we're going to work through several series problems step by step. And the big idea for this topic is this. Series are much more about pattern recognition than they are about big calculations. A lot of students get overwhelmed because the notation can look unfamiliar, especially with the sigma notation, power series, or Maclaurin series. But most of the time, the real question is just, what kind of series is this? Once you identify the pattern, you usually already know the main test, formula, or conclusion. So, as we go through these examples, keep asking, is this geometric? Is it a p-series? Is it alternating? Or is it a known Maclaurin series? So let's go problem by problem. So this first problem we have here is a geometric series. So, a geometric series has the form a plus ar squared plus ar cubed plus dot dot dot, where each term is multiplied by the same common ratio. Here, the first term is 3. To find the ratio, divide a term by the one before it. So we can do 9 divided by 3, which is equal to 3, and 27 divided by 9 is equal to 3. And so the common ratio is 3. So here's the rule. A geometric series converges only if this r value, the absolute value of this r value, is less than 1. But here, 3 is greater than 1. So the series does not converge, it diverges. So the answer is diverge. This is a very important first example. Once the ratio is bigger than 1 in an absolute value, the terms are getting larger, not smaller, so the series cannot settle to a finite sum. Let's go to the next problem. Okay, this is also geometric. The first term is 6, and now let's find the common ratio. Take 3 divided by 6, which is 1/2, or you can take 1.5 and divide that by 3, you get 1/2 as well. So r equals 1/2. And since 1/2 is less than 1, the series converges. And for a convergent geometric series, we're able to find the sum using the formula s equals a over 1 minus r. So let's plug in these values. So we get 6 over 1 minus 1/2. And once we simplify all this, we get the sum as 12. And this is one of the most useful formulas in series, but only when the absolute value of the ratio is less than 1. Let's go on to the next problem. So we're going to find the sum of 1 over n cubed. Now we move on to a p-series. A p-series has the form of some sort of sum of 1 over n to the power of p. And the rule is it converges if p is greater than 1, and it diverges if p is less than or equal to 1. So here p equals 3. Since 3 is greater than 1, this series converges. So the answer is convergence. This is a good reminder that you do not need the exact sum here. For many series questions, all you need is convergence or divergence rules. Let's go on to the next problem. This is another p-series. Here the exponent is 1. So this is the famous harmonic series. And the harmonic series always diverges. So even though the terms 1 over n goes to 0, the series itself still diverges. That means the answer is diverges. This is one of the most important examples in all of series because it teaches a major lesson. Just because the terms go to 0 does not automatically mean the series converges. Okay, let's go on to the next problem. So this one we have the sum of 4x to the power of n. Now we have a power series, and the goal is to find when it converges. This is actually a geometric series in disguise. You can think of this as the sum from n equals 0 to the infinity of 4x to the power of n. So the common ratio here is 4x, and for a geometric series to converge, we need the absolute value of r to be less than 1, like we said before. So here, that means that 4x must be less than 1. Now we divide both sides by 4. And we get x is less than 1/4. That's the key idea here. Whenever you see something raised to the nth power like this, Check whether it behaves like a geometric series. Alright, next question. So we're going to have the Maclaurin series for e to the power of 2x. And on the top right, we can see the formula for this. And the basic Maclaurin series for e to the power of x is e to the power of x equals sum from n equals 0 to infinity of x to the power of n over n factorial. So all you do is for e to the power of 2x, we just replace x with 2x. And you could also write out the first few terms if you wanted. So you get 1 plus 2x plus 2x squared over 2 factorial plus dot dot dot. And you get the sum from n equals 0 to infinity of 2x to the power of n over n factorial. And this is a great example of how known Maclaurin series are really just substitution patterns. Let's go on to the next problem. So we have cosine x. So this is another standard one you want to recognize immediately. The Maclaurin series for cosine is shown is cosine x equals 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial. So the answer is that. A couple important pattern notes. Only even powers appear, the signs start to alternate, and factorials are in the denominator. So if you want the sigma notation for this question, you can also write the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of 2n all over 2n factorial. Both forms are correct. This is one of the most common series to memorize because it shows up everywhere in calculus, and this goes the same for sine. And now we have an alternating series because of the factor negative 1 over n. If you guys want to pause this video and try it real quick, give you guys a few seconds for that. Okay, because of the alternating series, this causes the signs to switch back and forth. To test convergence, we use the alternating series test. That test says an alternating series converges if the absolute value of the terms decrease and the terms go to 0. Here, the absolute value of this term is 1 over n. And yes, 1 over n decreases as n gets larger. Also, we can test the limit. So the limit as n goes to infinity of 1 over n is 0. So both conditions are satisfied. This means that the series converges. A very important note here is that this series converges alternatingly. Even though the related non-alternating harmonic series, sum of 1 over n, diverges, that contrast is really worth remembering. So, the big takeaway from all these examples is this. With series, the hardest part is usually not the calculation, it's identification. You want to train yourself to look at a series and immediately ask, like, what pattern do I recognize? Like, is this geometric piece series alternating, or is it a known Maclaurin series? My recommendation is learning the sine, cosine, e to the power of x Maclaurin series. Because once you recognize the type, the test or formula usually becomes much more straightforward. So don't try to memorize every possible problem. Focus on recognizing the structure. That's what makes series manageable. Thanks for watching, and I'll see you guys in the next one.